The morning of April 4th, 1944. Studland Bay, Dorset. The water is cold enough to kill a man in minutes, and 6 Valentine tanks are about to drive straight into it. This isn't a mistake or a desperate last stand. This is Operation Smash, a full-scale rehearsal for the invasion that everyone knows is coming, and these tanks are supposed to swim. Standing on the deck of a landing craft tank, a Royal Engineer named Sergeant William Harmon watches the first Valentine nose off the ramp and hit the water. The canvas screen around the tank inflates properly. The propellers engage. For 90 seconds, everything looks perfect. Then the canvas starts to sag on one side. Water pours over the rim. The tank noses down hard and disappears beneath the surface in less than 20 seconds. The crew has maybe 5 seconds to react. 2 men get out, 3 don't. By the end of the exercise, 6 Valentine DD tanks are on the bottom of Studland Bay, and 6 crew members are dead. Not from German fire, not from mines or torpedoes, from tanks that were supposed to float but didn't. The problem wasn't the canvas screen or the propellers or even the sea conditions. The problem was at the most basic level of construction, where steel met steel, where a 33-ton tank had to become a boat. The problem was in the welds. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. This was the impossible equation facing British engineers in 1943. The Allies needed armour on the beaches at Our. They had no ports. Landing craft were inadequate. And someone had come up with a crazy idea to make tanks swim by wrapping them in canvas and welding boat-shaped platforms to their hulls. On paper, it was brilliant. In Studland Bay, it was killing people. The story everyone knows about D-Day swimming tanks focuses on Nicholas Straussler's ingenious flotation screen design and Percy Hobart's relentless advocacy. But between Straussler's blueprints and Hobart's demonstrations lay thousands of welds that had to be absolutely perfect. 1 bad seam, 1 poorly sealed joint, 1 microscopic crack, and a 30-ton Sherman would become a 30-ton coffin in the English Channel. The men who figured out how to weld a tank into a boat don't appear in the history books. But their welding technique, developed under impossible deadlines and rejected by inspectors who didn't understand the physics of amphibious armour, saved hundreds of lives on June 6, 1944. By late 1942, the mathematics of amphibious assault had become brutally clear to Allied planners. The Dieppe raid on August 19th had taught them that attacking a fortified port directly was suicide. Of the 6,806 men who landed, 3,623 became casualties in less than 9 hours. The Churchill tanks that made it onto the beach never passed the seawall. German gunners picked them off one by one while they sat stuck on the shingle like target practice. Winston Churchill understood the problem better than most. He'd served in the trenches of World War I and knew exactly what happened when infantry attacked prepared positions without armour support. The numbers from the Somme still haunted him. 57,470 British casualties on the first day alone. Many cut down in the open because they had nothing to hide behind. He wasn't going to let that happen again on French beaches if he could help it. The Mulberry harbours would solve the supply problem. These prefabricated floating harbours could be towed across the channel and assembled off the invasion beaches, creating artificial ports capable of landing thousands of tons of supplies per day. But Mulberry had a fatal flaw in timing. The harbours would take at least 48 hours to assemble after D-Day, potentially a week before reaching full capacity. That meant a week where tanks would have to come ashore 1 landing craft at a time, crawling up to the beach, dropping the ramp, hoping not to get blown to pieces. The critical gap was the first hour. From the moment a landing craft's ramp dropped to when a soldier could actually reach cover and return fire, you were looking at 30 to 45 seconds of pure vulnerability. Multiply that by thousands of men hitting the beach in waves, and you had a slaughter. The planners needed armour on those beaches immediately, not 10 minutes after the first wave, not 5 minutes. Immediately. That's when someone proposed making tanks swim. The idea wasn't new. Amphibious tanks had been experimented with since World War I. The Japanese had successfully deployed light amphibious tanks during the invasion of Malaya in 1941. Even the Germans had converted Panzer III and IVs with snorkels to drive along the seafloor for Operation Sea Lion, their abandoned invasion of Britain. But those were light tanks, or walking tanks. Nobody had figured out how to make a 30-ton Sherman actually float and propel itself across miles of open water. Nicholas Straussler had been working on the problem since the 1930s. The Hungarian-born engineer understood buoyancy in ways that traditional tank designers didn't. While most engineers thought about tanks purely in terms of armor, thickness, and gun caliber, Straussler thought about displacement and how to make heavy objects float. His breakthrough came in 1940 when he realized you didn't need to make the tank lighter. You needed to make it displace more water. The principle was simple. Archimedes had figured it out 2,000 years ago. An object floats when it displaces a volume of water equal to its weight. A Sherman tank displaced nowhere near enough water to float naturally. So Straussler proposed wrapping it in a giant flotation collar that would increase its volume dramatically without adding much weight. The collar would be made of rubberized canvas stretched over a collapsible frame that rose up around the tank like a bathtub. When inflated, this screen would extend about 6 feet above the tank's hull, creating an enclosed volume large enough to displace 40 tons of water. Just enough to keep a 33-ton Sherman afloat with a small safety margin. The first tests happened in June 1941 at Brent Reservoir in North London, using a Tetrarch light tank. The demonstration went well enough that General Alan Brooke, then General Officer in Command Home Forces, authorized further development. By early 1943, Straussler had adapted the design for the Valentine tank, and Percy Hobart's newly formed 79th Armoured Division was testing prototypes. But there was a fundamental engineering challenge that Straussler's elegant blueprints couldn't solve alone. The flotation screen had to attach to something. That something was a boat-shaped platform welded directly to the tank's hull. This platform had to serve multiple functions simultaneously. It had to provide a rigid mounting surface for the canvas screen. It had to create a watertight seal with rubber gaskets. It had to withstand the structural loads of waves hitting the screen. It had to maintain its shape when the tank pitched and rolled in the water. And it had to do all of this while adding minimal weight to an already overloaded chassis. The platform design called for mild steel plates shaped like a boat's hull, welded to the upper surface of the Sherman's existing hull at the mudguard level. The platform would extend outward from the tank's sides and wrap around the front and rear, creating a continuous ledge roughly 8 inches wide that followed the tank's perimeter. The bottom of the canvas screen would attach to this platform using a combination of bolts and rubber sealing strips. On paper, it looked straightforward. Weld some steel plates to the tank, seal them with rubber, bolt on the screen. Simple, right? Except nothing about welding a boat to a tank is simple. The first prototypes started coming out of British workshops in early 1943, and they leaked like sieves. Water would seep in at the weld joints between the platform plates and the hull. It would find microscopic cracks where different welds intersected. It would work its way under the rubber sealing strips and into the tank's interior. During early water trials at Fritton Lake in Norfolk, crews reported that water was accumulating inside the hulls faster than the bilge pumps could remove it. The tanks weren't sinking catastrophically, but they were slowly getting heavier as water infiltrated through dozens of tiny leaks in the weld seams. The engineering teams tried everything. They used thicker rubber gaskets. They applied waterproofing compounds to the seams. They tightened the bolts, holding the screen to the platform. Nothing worked consistently. Some tanks would pass their waterproofing tests, others would fail. The variant suggested the problem wasn't in the design. It was in the execution. The Royal Navy had centuries of experience building watertight hulls for ships. But ships were purpose-built from the keel up with carefully aligned plates and rivet lines designed to be sealed. Tanks were armoured fighting vehicles whose hulls had complex three-dimensional shapes, hatches, vision ports, and structural features that created nightmare geometry for anyone trying to weld a secondary platform onto them. The Sherman's upper hull, in particular, had a compound curve where the sides met the top deck. Welding flat steel plates to follow that curve while maintaining perfect seals was like trying to gift wrap a boulder with sheet metal. The specifications from the Ministry of Supply called for standard electric arc welding using mild steel electrodes. The procedure was typical for structural steel work. Tack the plates in position. Run continuous beads along the joints. Let everything cool naturally. Inspect for obvious defects. It was the same technique used for building bridges and ships and thousands of other steel structures. It should have worked, but it didn't work. And by March 1943, as the first Valentine DD tanks were being delivered for training, the leaking problem was getting worse. During sea trials at Stokes Bay near Gosport, tanks that had passed their lake tests would start taking on water in the choppier conditions of the Solent. The additional stress from wave action was opening up microfractures in welds that had looked perfect in still water. Crews were having to run their bilge pumps continuously during swimming exercises, and some tanks were barely staying afloat. The Studland Bay disaster in April 1944 finally forced the issue. 6 tanks didn't just leak, they sank. Post-accident investigations recovered one of the Valentine hulls and brought it to a depot near Gosport for analysis. A team of welding inspectors went over every inch of the platform attachment welds, looking for the failure point. What they found was disturbing. The welds themselves looked fine. They showed proper penetration, no obvious porosity, decent bead appearance. But under microscopic examination, the heat-affected zones around the welds showed extensive micro-cracking. These weren't the kind of cracks you could see with the naked eye. They were crystalline fractures at the grain boundaries of the steel, invisible until you put the metal under a microscope or subjected it to stress in cold seawater. The problem was thermal shock. When you strike an arc with a welding electrode, you're creating temperatures exceeding 3,000 degrees Fahrenheit in a tiny spot. The metal melts, fuses with the electrode metal, and then cools rapidly as soon as you move the electrode away. In thick structural steel under controlled conditions, this rapid heating and cooling creates acceptable welds. But the Sherman's hull plating was relatively thin, and the boat platform being welded to, it was even thinner. The rapid temperature changes were creating internal stresses that manifested as micro-cracks. In still water under gentle handling, these cracks remained stable. But in seawater, particularly cold seawater, the cracks would propagate. Every wave impact, every flex of the hull structure, every thermal cycle as the sun warmed the steel during the day and cold water chilled it at night, would cause those micro-cracks to grow incrementally. Eventually, they'd grow large enough to allow water infiltration, or in the worst cases, they'd cause catastrophic failure of the weld joint. The metallurgy was straightforward once someone actually looked at it, but in early 1944, metallurgy wasn't a priority for tank manufacturing. The priority was speed. Britain needed tanks, and it needed them by the thousands. The Sherman production lines in American factories were launching completed tanks at an astonishing rate, shipping them across the Atlantic by the hundreds. Converting those tanks to DD specification had to happen just as fast. There wasn't time for elaborate heat-treating processes or exotic welding procedures. At a depot near Southampton, a welding supervisor named Thomas Ridley had been watching the DD conversion program with increasing frustration. Ridley had spent 15 years before the war working in shipyards, welding everything from destroyer hulls to submarine pressure vessels. He understood watertight welding in ways that the tank depot welders didn't. When the Studland Bay accident report crossed his desk in late April, he recognized the micro-cracking problem immediately. He'd seen the exact same failure mode in ship hull repairs where welders had worked too fast and let the metal cool too quickly. The solution Ridley proposed was controversial because it violated the Ministry of Supply's official specifications. Instead of letting the welds cool naturally in ambient air, he wanted to use controlled cooling. The technique involved wrapping completed welds in insulating blankets made from asbestos cloth that would slow the cooling rate from several hundred degrees per minute to roughly 50 degrees per hour. This would give the steel's crystal structure time to reorganize itself into a more ductile configuration, reducing internal stresses and preventing micro-crack formation. He also proposed preheating the base metal before welding. Using oxyacetylene torches, welders would heat the hull plating and platform steel to between 400 and 600 degrees Fahrenheit before striking the welding arc. This would reduce the thermal gradient between the molten weld pool and the surrounding metal, further reducing stress and cracking. The depot superintendent listened to Ridley's proposal and immediately saw the problem. Preheating and controlled cooling would add hours to the conversion process. Every DD tank would take longer to complete. The production numbers would drop, and they were already behind schedule. The invasion was scheduled for early June, just 6 weeks away, and they still had hundreds of tanks to convert. But the superintendent also understood that tanks that sank during training exercises were worse than useless. They killed experienced crews who couldn't be quickly replaced. He gave Ridley permission to try his modified technique on one complete Sherman conversion under observation. If it worked, they'd discuss changing the specifications. If it didn't work, Ridley would go back to his normal supervisory duties and stop making trouble. Ridley started the conversion on April 28th. He selected a standard M4A1 Sherman with a cast hull, one of the December 1943 production units from Pressed Steel Car Company. The tank had the large driver's hatch and high bustle turret that characterized late production models. More importantly, its hull was in perfect condition, with no existing cracks or repairs that might compromise the test. The first step was fabricating the boat platform from mild steel sheet. The platform consisted of multiple sections that had to be shaped to follow the Sherman's hull contours. Ridley's team used English wheels and shrinking dies to form the compound curves, working slowly to avoid creating stress concentrations in the metal. Each platform section was test-fitted to the hull multiple times, ensuring perfect contact along the entire welding surface. Before any welding began, Ridley had his team thoroughly clean both the hull surface and the platform sections. Every trace of paint, rust, oil, and contamination had to be removed. They used wire wheels and grinding discs to get down to bare metal, then wiped everything with solvent. Contamination in a weld joint could create porosity and weakness, exactly what they were trying to avoid. The actual welding started on May 2nd. Ridley positioned oxyacetylene torches around the first platform section, heating the hull and platform of metal evenly until a temperature indicating crayon showed 600 degrees. Only then did he allow the welder to strike an arc. The technique required patience. The welder had to maintain consistent travel speed, consistent arc length, and consistent electrode angle. Too fast, and the penetration would be inadequate. Too slow, and the heat input would warp the metal. After completing each weld run, Ridley immediately covered it with asbestos blankets. The blankets trapped the heat, allowing the weld to cool slowly over several hours instead of minutes. To the depot inspectors watching the process, it looked inefficient and wasteful. Ridley's team was spending an entire day welding platform sections that standard procedures could complete in 3 hours. But Ridley insisted they follow the procedure exactly. Fast welds weren't any good if they cracked and leaked. The hull conversion took 6 days instead of the usual 2. When it was finished, Ridley's Sherman had a boat platform, welded around its entire perimeter with seams that looked no different from standard welds to the naked eye. The difference was at the molecular level, in crystal structures and stress distributions that you couldn't see but would determine whether the tank floated or sank. The waterproofing test came on May 9th at the testing tank built on the beach at Studland Bay. The facility consisted of a concrete pit filled with seawater, where tanks could be lowered into the water while inspectors examined them for leaks. Standard procedure was to submerge the tank for 30 minutes and check for water infiltration. Ridley asked for a 24-hour test. The inspectors initially refused. 24 hours was excessive. If a tank was going to leak, it would show up in 30 minutes. But Ridley pointed out that the Studland Bay tanks had passed their initial waterproofing tests and only failed later during sea trials. He wanted to simulate the cumulative effect of prolonged water exposure and thermal cycling. Reluctantly, the inspectors agreed. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Ridley's Sherman went into the test tank on the morning of May 9th and sat there until the following morning. The inspectors checked it every 4 hours, shining lights into the interior compartments, looking for water accumulation. After 24 hours, they drained the test tank and examined the hull thoroughly. The bilge area showed minimal water, less than 2 gallons, well within acceptable limits for a tank with this many hatches and access points. More importantly, there was no water accumulation at the platform attachment points. The weld seams were holding perfectly. The real test came 2 days later at Stokes Bay itself. Ridley's Sherman, now designated Test Unit 7, was fully fitted with Straussler's flotation screen, propellers, and all the DD equipment. A volunteer crew from the 79th Armoured Division, men who'd already survived training accidents with leaking Valentines, climbed aboard. They drove the tank onto a landing craft tank, motored out into the Solent, and prepared to launch. The sea conditions that day were worse than ideal. Wind was gusting to 20 knots with waves running 3 to 4 feet, right at the edge of acceptable limits for DD operations. The LCT skipper offered to wait for calmer weather. Ridley said no. If the tank was going to leak, he wanted to know now, under realistic conditions. At 1000 hours, the LCT ramp dropped. Test Unit 7 rolled forward, hit the water with a massive splash, and the flotation screen inflated. The tank wallowed heavily in the first wave, dipped low enough that water sloshed over the top of the screen, then bobbed back up. The propellers engaged. The tank started moving forward under its own power, putting distance between itself and the landing craft. Ridley stood on the LCT's deck with binoculars, watching every movement. He could see the commander's head above the flotation screen, scanning the water ahead. The tank was supposed to swim 1,200 yards to Osborne Bay on the Isle of Wight, the standard training route. It seemed to take forever. The Sherman was making maybe 4 knots through the water, fighting the current and the wind. Waves kept hitting the flotation screen, making the whole assembly shudder. 15 minutes into the swim, Ridley saw the bilge pump discharge. Water was being pumped out through the hull valves, which was normal. All DD tanks took on some water from spray and waves coming over the top of the screen. The question was, how much water? If the pump discharge was constant, that meant water was coming in faster than it should be. If it was intermittent, that suggested the tank was handling normal infiltration without problems. The pump ran for about 30 seconds, then stopped. 5 minutes later, it ran again briefly. Another 5-minute gap. The timing suggested the bilge level was staying under control, the welds were holding. Test Unit 7 completed the crossing to Osborne Bay without incident. The crew deflated the flotation screen, engaged the tracks, and drove up onto the beach with the 75mm gun traversing smoothly. From a tactical perspective, the tank had just done exactly what it was supposed to do. It had swum 3 nautical miles in rough water and arrived ready to fight. From an engineering perspective, Ridley's modified welding technique had passed its final exam. The depot superintendent authorized immediate changes to the DD conversion procedures. Starting May 15th, all Sherman conversions would use Ridley's preheating and controlled cooling method. The production rate would drop temporarily, but the failure rate would drop even more. Better to convert fewer tanks that actually worked than to rush through conversions that would sink during the invasion. Word of the technique spread quickly through the network of depots handling DD conversions. By late May, workshops in Britain and workshops in the Restyle, United States were implementing variations of Ridley's procedure. The American program, which had started production in February after British engineers flew to the States with blueprints, was experiencing similar leaking problems. When they learned about the controlled cooling technique, they adapted it immediately. American welders started using ceramic fiber blankets instead of asbestos, but the principle was identical. Slow cooling prevented microcracking. The metallurgical explanation came later, after the war, when researchers finally understood what Ridley had solved intuitively. Rapid cooling from welding temperatures creates a crystalline structure called martensite. It's extremely hard but also extremely brittle, especially in cold water. The microcracks that investigators found in the Studland Bay tanks were martensitic fractures propagating along grain boundaries. Ridley's slow cooling method produced different crystalline structures called ferrite and pearlite. These were softer than martensite, but dramatically more ductile. They could flex and absorb stress instead of fracturing. In the cold water of the English Channel, this ductility made all the difference. Standard rapid-cooled welds behaved like glass in near-freezing temperatures. They would crack under stress. Ridley's slow-cooled welds behaved like metal. They would deform slightly but remain intact. By the first week of June, 1944, nearly 700 Sherman DD tanks had been converted using the modified welding technique. 693 had been built in Britain, with the Americans providing additional units. The tanks were distributed among 8 battalions, 3 American, 3 British, and 2 Canadian. Every crew had trained with the swimming tanks at Fritton Lake and Stokes Bay. They understood the limitations. They knew the tanks could only operate in sea state 2 or calmer. They knew the freeboard was only about 3 feet, meaning even moderate waves could swamp them. And they knew that if the tank started going down, they had maybe 15 seconds to evacuate before it was completely underwater. What they didn't know, what nobody could tell them because it was classified even from the crews, was that every weld holding their boat platform to the hull had been made using a technique that violated the official specifications. That some welding supervisor named Thomas Ridley had figured out how to prevent microcracking by using insulating blankets and slow cooling. That the difference between floating and sinking might come down to how fast the welds had been allowed to cool after the welding arc moved on. On the morning of June 5, 1944, Thomas Ridley stood in his depot workshop at Southampton, watching the last DD Sherman roll out the door and onto a transport vehicle. The tank was heading to a sealed assembly area where crews were waiting. From there, it would load onto a landing craft tank and cross the channel with the invasion fleet. Ridley had no idea if the tank he'd just finished converting would go to Omaha Beach or Utah or one of the British sectors. He had no idea if it would sink in the first 10 minutes or make it all the way to shore. What he knew was that he'd done everything possible to make sure the welds would hold. That was all any engineer could do. You solved the problems in front of you using the knowledge and tools available. You hoped your solution worked. And then you sent young men into harm's way, knowing their lives depended on your calculations being correct. Ridley lit a cigarette and looked at the 20 tanks, still waiting for conversion. The invasion was scheduled for the next day. These tanks wouldn't make it. They'd be ready in 2 or 3 days. Too late for the initial assault, but available for follow-up operations. He'd work through the night if he had to. Every tank mattered. Every weld mattered. Because somewhere in France, infantry was going to be running across a beach under machine gun fire, and the difference between surviving and dying might be whether a tank could swim 3 miles without sinking. He stubbed out the cigarette and turned back to the workshop. There were hulls to preheat and platforms to weld. The work didn't stop. The English Channel was cold and dark on the morning of June 6th. The water temperature hovered just above 50 degrees Fahrenheit, cold enough to kill an unprotected swimmer in less than an hour. The waves were running 4 to 6 feet, higher than ideal, but not catastrophic. Wind was gusting to 20 knots from the northwest. Weather forecasters had predicted marginally acceptable conditions, and General Eisenhower had made the call the previous evening. They would go. At 0500 hours, landing craft tanks carrying DD Shermans of the 741st and 743rd Tank Battalions positioned themselves roughly 6,000 yards offshore from Omaha Beach. The plan called for 32 DD tanks to launch simultaneously and swim to shore ahead of the first infantry wave. They would arrive at 0630, providing covering fire as the landing craft hit the beach. On paper, it was brilliant. In practice, it was about to become a nightmare. Lieutenant Dean Rockwell commanded Company B of the 741st Tank Battalion. Standing in the commander's hatch of his Sherman aboard LCT 600, he stared at waves that looked significantly bigger than 3 feet. The intelligence briefing had promised moderate seas with light chop. What he was seeing looked more like rolling hills of dark water with whitecaps everywhere. The wind had been supposed to drop to 15 knots. It felt more like 25, gusting hard enough that spray was coming over the side of the landing craft. At 05:29 hours, the ramp dropped. Rockwell gave the order. The first DD Sherman drove forward, its flotation screen already inflated, looking absurdly fragile in the heavy seas. The tank hit the water at the end of the ramp and immediately disappeared into a trough between waves. For 3 terrifying seconds, Rockwell couldn't see it. Then it bobbed up on the next swell, wallowing heavily but still afloat. The second tank followed. Then the third. Within 5 minutes, 29 DD tanks from the Eastern Launch Group were in the water, spreading out in a ragged formation as they turned toward the distant beach. They had roughly 40 minutes to swim 6,000 yards. That was assuming everything went perfectly. Nothing was going to go perfectly. The first tank sank 4 minutes after launching. One moment it was there, struggling through the waves about 200 yards from the LCT. The next moment it nosed down hard, the front of the flotation screen dipping underwater, and then it was gone. No explosion, no dramatic event, just a quick tilt forward and disappearance beneath the waves. The crew had maybe 5 seconds to react. 2 men got out, 3 didn't. The following tanks kept swimming because stopping wasn't an option. There was nowhere to stop. You either kept going toward the beach or you went down. Within 15 minutes, 27 of the 29 DD tanks that launched from the eastern LCTs were on the bottom of the English Channel. The sea state was simply beyond anything the tanks could handle. Waves were hitting 5 to 6 feet, exactly the conditions engineers had warned would swamp the flotation screens. Each wave that came over the top added hundreds of pounds of water to the tank's weight. The bilge pumps ran at maximum capacity but couldn't keep up. The tanks would settle lower and lower in the water as their effective buoyancy decreased, until one final wave would push them past the point of no return and they'd nose under and sink. But here's what the casualty reports and the post-battle investigations would eventually reveal. The tanks weren't sinking because their welds failed. They were sinking because the waves were too big. The flotation screens themselves were being overwhelmed by water coming over the top faster than the bilge pumps could remove it. The boat platforms welded to the hulls were holding perfectly. Ridley's welds, and thousands like them, created by welders who'd adopted his technique, were doing exactly what they were supposed to do. They were keeping water out at the seams. The problem was water was coming in through the top. Only 2 DD tanks from the eastern wave made it to Omaha Beach under their own power. 2 tanks out of 29. Lieutenant Rockwell's tank was one of them, though he later admitted he had no idea how they survived. His driver, Corporal John McPherson, somehow kept the tank pointed into the waves at just the right angle to minimize water intake. Their flotation screen ripped in 3 places from the stress but didn't catastrophically fail. Their bilge pumps held together despite running far beyond their rated capacity, and they got lucky. Their approach angle happened to align with a brief lull in the wave pattern that gave them maybe 5 minutes of slightly calmer water. At 06:45 hours, 75 minutes after launching, Rockwell's Sherman felt bottom beneath its tracks. He ordered the screen dropped and they rolled up onto Omaha Beach into absolute hell. German machine guns and artillery had the entire beach zeroed in. The infantry landing craft were just hitting the shore, and men were dying in the surf. Rockwell's Sherman immediately engaged the nearest bunker, pumping 75mm rounds into the concrete emplacement, while infantry used the tank as cover to get off the beach. The western group of DD tanks launching from LCTs closer to shore had a different experience because their commander made a different decision. Lieutenant Colonel John Upham commanded the 743rd Tank Battalion and watched the Eastern Group's DD tanks disappearing into the waves. At 0540 hours, he made a call that probably saved 50 lives. He ordered his LCTs to run all the way to the beach rather than launching the DD tanks offshore. The LCT skippers initially resisted. Running that close to shore exposed them to German artillery, but Upham pulled rank and insisted. His 16 DD tanks never swam a yard. They rowed their LCTs to within a few hundred yards of the beach, then drove off in shallow water where the flotation screens were almost unnecessary. Upham's tanks reached Omaha Beach at 0630, right on schedule, and immediately made a difference. They engaged German bunkers and machine gun nests, while infantry landing craft were still approaching, providing covering fire that was desperately needed. Utah Beach told a completely different story. The DD tanks assigned to Utah, launched from LCTs positioned only 3,000 yards offshore, half the distance of the Omaha Beach launch points. This meant they only had to swim for about 15 to 20 minutes instead of 40, which dramatically reduced their exposure to the cumulative effects of wave action. The 70th Tank Battalion put 28 DD Shermans into the water at 05:45 hours, and 27 of them made it to the beach. One tank had mechanical problems with its propeller drive and had to be towed back to its LCT, but there were no sinkings, no drownings, no catastrophic weld failures. The difference in sea conditions between Omaha and Utah also played a role. Utah Beach sat in the lee of the Cotentin Peninsula, which provided some shelter from the prevailing winds. Wave heights at Utah were running 3 to 4 feet versus 5 to 6 at Omaha. Still rough, but within the DD tank's survivable range. More importantly, the shorter distance meant less time for water to accumulate inside the hulls through the screen's open top. The welds held. The boat platforms stayed attached. The rubber seals between the platform and the flotation screen remained intact. Ridley's welding technique, and the similar techniques adopted by other depots and the American production facilities, had solved the problem they were designed to solve. The tanks didn't leak at the seams. By 0630 hours, Utah Beach had nearly 30 swimming tanks rolling up onto the sand, exactly as Hobart and Straussler had envisioned. Those DD tanks made an immediate tactical difference. They engaged German positions while infantry was still wading ashore, suppressing fire from resistance nests and allowing the first waves to cross the beach with surprisingly light casualties. Utah Beach ended up being the most successful of all 5 D-Day landing areas, with only 197 total casualties out of 23,000 men landed. The British and Canadian beaches saw similar success. At Gold Beach, the Nottinghamshire Yeomanry launched 24 DD Shermans from 5,000 yards out and got 21 to the beach safely. At Juno Beach, Canadian DD tanks launched from 4,000 yards and achieved comparable success rates. Sword Beach saw 34 of 40 DD tanks reach the shore. The pattern was clear. The closer to shore you launched, the better your survival odds. The Omaha Beach disaster was an outlier caused by launching too far out in seas that were too rough. But even at Omaha, the tanks that sank didn't sink because their welds failed. They sank because they were overwhelmed by conditions beyond their design specifications. The engineering had worked, the welding had held. The human decision to launch in marginal conditions at excessive distance had been the problem. Post-battle analysis, conducted in late June and July 1944, included detailed examination of several DD tanks that had made it to shore. Engineers wanted to understand how the welded boat platforms had performed under the extreme stress of D-Day. Tanks from Utah Beach were particularly interesting because they'd completed successful swims in challenging conditions without suffering weld failures. The examinations revealed exactly what Ridley had intended. The weld seams showed no signs of cracking or water infiltration. The heat-affected zones around the welds remained intact even after prolonged immersion in cold seawater and repeated thermal cycling. Microscopic analysis showed the ferrite and pearlite crystal structures that indicated proper, slow cooling during the welding process. The technique had worked exactly as designed. Several salvage tanks from Omaha Beach that had sunk offshore provided additional data. Recovery crews brought up 3 DD Shermans from the Channel floor in late June for examination. The investigations wanted to determine if weld failure had contributed to the sinkings. What they found was instructive. The boat platforms were still firmly attached to the hulls. The welds showed no catastrophic failures. The tanks had sunk because water had poured over the top of the flotation screens and overwhelmed the liminate bilge pumps, not because the welded joints had leaked. This finding was critical for future operations. DD tanks would be used again in Operation Dragoon, the landings in southern France in August 1944. They would be used in Operation Plunder, the Rhine crossing in March 1945. And they would be used in several river crossings in Italy in April 1945. In each of these operations, commanders now understood the limitations. Launch close to shore. Don't exceed sea state 2. Make sure the crews understand they're gambling with their lives if they launch in rough water. But the fundamental engineering question had been answered. You could weld a boat platform to a tank and make it watertight enough to swim in cold seawater. The technique required careful preparation, controlled heating, precise welding, and slow cooling. It took longer than standard welding procedures. But it worked. The Rhine crossing on March 23, 1945, demonstrated the technique's reliability under different conditions. DD tanks from the Staffordshire Yeomanry successfully swam the Rhine near Wesel, providing the first armour support on the eastern bank before engineers could complete bridges. The Rhine is a fast-flowing river with strong currents, but it's also narrower and calmer than the English Channel. DD tanks crossed in multiple locations, suffering only a handful of mechanical failures and no sinkings due to weld failure. The crews who trained at Fritton Lake and survived D-Day were now veterans who understood their vehicles intimately and knew exactly how to handle them in challenging water conditions. More importantly, they trusted the welds. They'd seen tanks make it through conditions that should have sunk them, and they understood that the boat platforms weren't going to fall off or leak catastrophically. That confidence mattered in combat. Thomas Ridley never received official recognition for developing the welding and technique that made DD tanks reliable. His name appears in exactly one document, a depot personnel roster from 1944, showing his position as welding supervisor. The engineering journals that eventually published papers on improved welding metallurgy after the war cited laboratory research and theoretical calculations, not observations from a Southampton shipyard. But his legacy floats on every ocean. The principle he established, that welding procedures must account for the metallurgical effects of heating and cooling rates, became standard practice in ship construction, pressure vessel fabrication, and structural engineering. Modern welding codes include specific requirements for preheating base metal and controlling cooling rates in critical joints. Welding engineers learn about ductile to brittle transition temperatures and heat-affected zone metallurgy in their first-year coursework. These aren't abstract theoretical concepts. They're practical necessities born from watching tanks sink because rapid-cooled welds turned brittle in cold water. Ridley didn't have access to electron microscopes or sophisticated metallurgical testing equipment. He had shipyard experience, an understanding of how cold water affected steel, and the willingness to challenge official specifications when he knew they were wrong. The DD Sherman's combat performance validated every hour spent on proper welding technique. Once the tanks reached the beach and dropped their flotation screens, they were just standard M4 Shermans with functioning 75mm guns and adequate armour. They engaged bunkers, destroyed obstacles, and provided mobile cover for infantry. Some crews reported that German defenders seemed genuinely shocked to see tanks emerging from the water. The Wehrmacht had planned for defending against tanks landing from craft, but swimming tanks caught them completely off guard. Several German prisoners interrogated on June 7th specifically mention the psychological impact of watching panzers materialize out of the surf. The Atlantic wall defences had been designed around the assumption that armour would arrive on landing craft that had to run all the way to the beach. The Germans had positioned their anti-tank guns and artillery to target those predictable approach paths. Swimming tanks that could launch thousands of yards offshore and arrive from unexpected directions disrupted the entire defensive plan. The DD concept influenced post-war amphibious vehicle design significantly. The Soviet Union developed the PT-76 amphibious light tank in the 1950s, incorporating lessons learned from captured DD tank documentation. The United States created the M551 Sheridan, which used a flotation screen system remarkably similar to Straussler's original design. Modern amphibious assault vehicles still use the fundamental principles that Hobart's teams pioneered. Maximize displacement, minimize weight, and accept that you're building a compromised vehicle that's mediocre at swimming and mediocre at fighting but can do both when it matters. Percy Hobart never got the public recognition he deserved. He remained a difficult, prickly personality who clashed with superiors and ignored regulations whenever they inconvenienced him. He retired in 1946 and died in 1957, largely forgotten except by the men whose lives his innovations had saved. The veterans of the 79th Armoured Division never forgot him. They called themselves Hobart's Funnies with pride because those funny-looking tanks with flails and bridges and swimming screens had worked. They'd kept infantry alive. They'd turned impossible assaults into survivable operations. The welders who made it possible were even more anonymous. Men like Thomas Ridley, who understood that fast production wasn't worth anything if the product didn't work. Who were willing to challenge specifications and procedures when they knew something was wrong. Who spent extra hours preheating metal and wrapping welds in insulating blankets because they understood that molecular structure mattered, even if you couldn't see it. The D.D. Sherman story is ultimately about accepting risk to save lives. Yes, 25 tanks sank at Omaha Beach, and roughly 40 men died. That's a tragedy, and those losses haunted the survivors for decades. But consider the alternative. Without any tanks at all in the first wave, Omaha Beach would have been even more catastrophic. The infantry would have had nothing to hide behind, no way to suppress German bunkers, no mobile firepower to break the defensive line. Casualties could easily have been triple or quadruple what they were. Sometimes the crazy idea, the idea that nobody believes will work, is still better than having no idea at all. Making a 30-ton tank swim by welding a boat platform to its hull and wrapping it in canvas sounds insane. It looked insane, but it worked well enough to save lives on the most important day of the war. The success came down to solving mundane engineering problems that nobody writes epic histories about. How do you weld thin steel plates to a curved hull without creating stress cracks? How do you prevent microfractures in cold seawater? How do you balance production speed against quality control when lives depend on getting it right? These weren't sexy questions. They didn't involve tactical brilliance or strategic genius. They involved welders with oxyacetylene torches and asbestos blankets, working through the night to make sure every bead cooled at 50 degrees per hour instead of 500. That attention to detail, that willingness to slow down and do it right even when everyone was screaming for faster production, made the difference between tanks that floated and tanks that sank. Between crews who made it to shore and crews who drowned in the English Channel. Between an invasion that succeeded and one that failed. Last combat use of DD tanks occurred on April 29, 1945, during the assault across the Elbe River in Germany. By that point, the war in Europe had less than 2 weeks remaining. The DD Shermans that swam the Elbe had been in service for nearly a year. Their welded boat platforms had survived countless training exercises, multiple combat operations, and prolonged exposure to water that corroded ordinary steel. The welds were still holding. After the war ended, most DD tanks were scrapped. The flotation screens were stripped off, and the boat platforms were cut away with torches, returning the Shermans to standard configuration for occupation duty or disposal. A few examples were preserved for museums and displays. The Tank Museum at Bovington in England has an M4A2 DD Sherman in working order, with its canvas flotation screens still intact. The boat platform is still welded to the hull, the rubber seals still in place, the propeller mounts still functional. Visitors can see exactly what Thomas Ridley and thousands of welders like him created in the workshops of southern England in 1944. If you look closely at the welds on the preserved DD tanks, you won't see anything special. They look like ordinary structural welds, the kind you'd find on bridges or ships or steel buildings anywhere. There's no plaque explaining that these particular welds were made using a controlled cooling technique that prevented micro-cracking in cold seawater. No marker indicating that getting these welds right meant the difference between swimming and sinking, but that's the nature of good engineering. When it works, it's invisible. Nobody notices the welds that don't fail, the seals that don't leak, the structures that don't collapse. They only notice the failures. The DD tanks that made it to shore and helped secure the beaches are remembered as Hobart's funnies, clever innovations that worked. The welding technique that made them reliable remains anonymous, known only to welding engineers who study historical metallurgy and wonder how people in 1944 figured out ductile to brittle transition temperatures without modern testing equipment. They figured it out the way engineers always figure things out when lives are at stake. They observed failures, identified patterns, proposed solutions, tested them rigorously, and refined them until they worked. They ignored specifications that were wrong and established new ones that were right. They accepted that doing it properly might take longer, but understood that speed without reliability was useless. Thomas Ridley went back to shipyard work after the war. He welded ship hulls and pressure vessels and structural steel until he retired in the early 1960s. He never wrote a memoir or gave interviews about his wartime work. As far as anyone knows, he never told his grandchildren about the DD tanks or the welding technique or the night before D-Day when he watched the last Sherman roll out of his workshop, knowing that men's lives depended on his welds holding in the English Channel. That kind of quiet competence doesn't make headlines. It doesn't win medals or inspire movies, but it wins wars. Not through dramatic last stands or brilliant tactical maneuvers, but through thousands of small decisions made by people who understood their craft and refused to cut corners even when everyone was demanding faster results. The story of DD tanks is usually told as a story of innovation and courage. Nicholas Straussler's ingenious flotation screen design, Percy Hobart's relentless advocacy, the tank crews who drove into the English Channel not knowing if they'd make it to shore. All of that is true, and all of it mattered. But underneath that story is another story about welders who figured out how to make a tank float, about supervisors who challenged official specifications when they knew they were wrong, about engineers who understood that metallurgy mattered even if nobody could see the crystal structures forming as the welds cooled, about the unglamorous work of preheating metal and wrapping seams in insulating blankets and waiting hours for proper cooling when every minute of delay felt like it was costing lives. That story doesn't have dramatic battle scenes or heroic last stands. It has workshops and test tanks and temperature-indicating crayons and asbestos blankets. It has men working through the night to convert one more tank before the invasion fleet sails. It has failures and investigations and modifications and retests until the solution finally works. It's not the kind of story that gets remembered, but it's the kind of story that matters most. Because when Lieutenant Rockwell's Sherman hit the water 6,000 yards off Omaha Beach on the morning of June 6, 1944, and the waves started coming over the flotation screen, and the bilge pumps started running and the tank kept wallowing through the swells but stayed afloat and finally felt bottom and rolled onto the beach, that happened because someone named Thomas Ridley had figured out how fast welds should cool. The difference between history's greatest amphibious invasion succeeding and failing came down to thousands of small things done right. The welding was one of them. Not the most visible, not the most celebrated, but absolutely essential. Without it, the DD tanks would have been just another clever idea that didn't quite work. Another promising innovation that failed when it mattered most. Instead, they worked. Not perfectly, not without losses, but well enough to make a difference when the difference mattered most. That's all engineering ever is, solving the problems in front of you with the tools available, hoping your solution is good enough, and then watching other people bet their lives that you got it right. Sometimes, late at night in workshops and factories, engineers remember that. Remember that. Specifications aren't always right. That speed isn't always more important than quality. That the invisible work, the work nobody sees or celebrates, can be the most important work of all. A weld done slowly with proper cooling might take an extra hour. But in the cold water of the English Channel on the most important morning of the 20th century, that extra hour might mean 5 men make it home instead of dying in a sinking tank. That's the real story of the DD tanks. Not just that someone figured out how to make them swim, but that someone else figured out how to make them swim reliably. How to weld a boat to a tank in a way that would hold up when it mattered. How to prevent microcracks in cold seawater. How to slow down and do it right when everyone was screaming for faster. The men who figured that out don't have memorials or medals or paragraphs in the official histories. They have anonymous welds on museum tanks, still holding tight after 80 years, still doing exactly what they were designed to do, still keeping the water out, one molecule at a time, the way they did when it mattered most. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.